learned a little bit about current, voltage, and resistance in circuits. We've also seen examples of how capacitors can be put into series and parallel and more complex arrangements in a circuit. So what we're going to do is we're going to bring those concepts to our resistors and then start looking at more complex circuits, including circuits that have multiple resistors. We'll have circuits that have resistors and capacitors. And then finally, we will introduce inductors, which are electromagnets, and put those into circuits and see how our circuits kind of change in these different arrangements and over time. When we go to analyze circuits, there are two fundamental rules that apply to circuits: Kirchhoff's loop rule and Kirchhoff's junction rule. Sometimes you've heard them called laws instead. They're not strict laws, which is why rules are kind of a better way to approach kind of the theory behind this, because there's a lot of assumptions that have to be made in order for these to work. So Kirchhoff's loop rule basically tells us that the sum of the voltage rises and the voltage drops must equal 0. So if you were to kind of create a loop around the circuit, your voltage rises are caused by your voltage sources, such as like a battery, and your voltage drops would be caused by devices that convert kind of electrical energy into other forms. So a resistor would cause a voltage drop. So if you were to add up all the rises and all the drops along a single loop in a circuit, then those must add up to 0. This is actually a statement of conservation of energy, because remember that our potential energy is a test charge times the potential. So if you were to take a charge and move it from the battery, one side of the battery, through the circuit to the other side, you cannot create or destroy energy. So if our battery is creating a source of energy, then our resistors have to be removing that energy so that we have no net change in energy. The second one is Kirchhoff's junction rule, and it's related to current. So it says the sum of the current into a junction is equal to the sum of the current out of a junction. So a junction is going to be anywhere where wires split off or come together. So current in must equal current out. So in this example picture, you have current I1 going into a junction and I2 and I3 coming out of the junction. This is a statement of conservation of charge. So we've seen conservation of charge in a couple other situations. So this is a formal application of that in circuits. The other concept we have to kind of think of is the idea of equivalent resistance. We have seen equivalent capacitance. And so what equivalent resistance is if you were to take all of the components in a circuit that have resistance, so in this case R1, R2, and R3, those are all adding up to create some particular current that is coming out of that power supply. So with that same power supply as we have in the original situation, if you could combine the effect of all of those resistors into a single component, that equivalent resistance would give the exact same current as in the original circuit. That's what equivalent resistance is. Kind of similar to our idea of equivalent capacitance. So when we look at series versus parallel circuits, and we're going to learn how you can apply these concepts of the junction and loop rules for Kirchhoff and equivalent resistance, and then eventually capacitance and so forth into analyzing circuits. So with our series circuit, remember that a series circuit is going to have a single loop, and every component has to be in that loop. If we were using light bulbs, if you remove one of the bulbs, all other components in the circuit would go out. So all the bulbs would go out, there'd be no current flowing. In parallel circuits, you have multiple paths for the current to flow. So for example, you could flow directly from the battery and go along this outer loop that goes into the wire, back in through this outer one, and comes in towards the center. Or you could do this inner loop and come in just towards this inner light bulb right there. You also have a loop that involves just these components, but we don't normally do a lot analyzing those loops because they don't contain the battery, and it gets a little wonky. Now, because there are multiple paths, if you remove one of the bulbs, the other bulb is going to remain lit because there is still a path directly from the battery through that component without having to worry about the one that was removed. So in our series circuit, you are going to have a single loop. So we could take this circuit with 2 light bulbs and represent those light bulbs as resistors in the circuit diagram below. And so then we've got our battery and we got our potential V0 for that battery. So according to Kirchhoff's junction rule, current in is equal to current out of any single junction. So if we assume that I0 is the current draw from the power supply, that current draw is coming in to this resistor right here. So you could look at like this little corner of the wire, and well, I0 has to be coming into that location. Now we usually define the currents and voltages resistance to match our resistors. So there's going to be some current I1 going through R1. There's going to be some current I2 going through R2. But because of Kirchhoff's junction rule, there really aren't any junctions. There's no point where there is a split in the wire. So that means every point along this wire has to have the same current. So I1 has to equal I0 because what's coming into this point is I0. What's leaving that point is I1. Those have to be the same because the current doesn't split. Similarly, when you take this point right here, you have I1 coming in, but I1 is the same thing as I0. You have I2 coming out, so there's no split, so that means I2 must also equal I0. When you get to this point here, we still aren't splitting, but I know that when I get to my power supply, there's no junction there either, so what is leaving my power supply has to be the same as what is coming into my power supply. So this branch here also has to be I0. So that means the current everywhere has to be I0. So I0 must equal I1, which must equal I2. So what this kind of tells me, if you think back to measurements in circuits, if I was to put an ammeter here, here, or here, all of those ammeters would have to read the exact same value. Otherwise, we'd have more charge going into one part of the circuit than is leaving another, and that doesn't work. Now, when we look at the voltages, when we are using Kirchhoff's loop rule, our sum of our voltage rises and our drops has to be 0. So in this circuit, we're going to have a voltage rise caused by the power supply. That is going to be a source of our voltage. When we have the resistors, our resistors are going to be voltage drops. Additionally, light bulbs will be voltage drops, motors, all sorts of different things will cause voltage drops. We will see that components like capacitors and inductors can sometimes act like voltage rises or drops. So we're going to leave those out of the conversation for right now because that's a little bit more complicated. So what you do is you choose a loop direction that is in the same direction of the current. So we know that I0 from conventional current is going to leave the positive side of the power supply and then go around, in this case, in a clockwise direction. So that is going to be the direction of my loop. You have to choose a loop direction, or in some cases, there will be a loop direction chosen for you. You'll see that when you get to the derivation packets, that in some cases I give you loops, and in other cases you have to choose your own loops. And the way you draw your loop can affect the way that your equations come out. So we're going to use this loop that is drawn. Let me clear this ink really quickly. So in this case, our battery is creating a voltage drop. So it's going to be a positive V0. And the voltage drops across R1 and R2 are going to be negative because they're drops. So we're going to write negative V1 and negative V2. So we could write an equation that says our voltage rise plus our voltage drops, and our voltage drops are negative because they're causing a loss of energy, has to add up to 0. So what this tells me is that V0 is equal to V1 plus V2. So this tells me that the voltage drop from my individual components will add up to the voltage of the battery. You have to make sure that you read it like this. If I was to add another component, if I was to add another resistor in here, R3, V0 is still going to be the same, but if I add in another component, all of this would still have to add up to V0, so that means that V1 and V2 would likely have to get smaller if I was to add in a third component. So the voltage drops from the individual components add up to the battery voltage whenever you're in series. So what we can do is we can take what we have just learned and we can figure out the equivalent resistance in a series circuit. So we have some current I0 coming out of our power supply with our voltage source V0. We have R1 and we have R2. In series, our equivalent resistance is going to be the sum R1 plus R2. So let me show you where this comes from. So picture that I have my overall circuit. My overall circuit is going to follow the loop rule. So I have V0 is equal to V1 plus V2. Now with Ohm's law, I know that V is equal to I times R. What that means is I can write statements that say V0 is equal to I0 times Req. I can say that V1 is equal to I1 times R1, and V2 is equal to I2 times R2. All of these are valid statements of Ohm's law. So I can sub those in to my equation for Kirchhoff's loop rule. So I'm going to get that V0 is I0 times Req. V1 is I1 times R1. And V2 is I2 times R2. I also know from the junction rule that I0 is equal to I1, which is equal to I2. So I can replace I1 with I0 and I2 with I0. And then what happens is I get I0 Req is equal to I0 R1 plus I0 R2. And if I was to divide out this whole equation by I0, I get that Req is equal to R1 plus R2. And that if I was to repeat this with even more components, I'm still going to end up with this just adding up. So the more components I add into my loop, the larger the equivalent resistance is going to be. So according to our equivalent resistance for series, the more resistors you add in series, the larger the resistance in the circuit is increasing. Now we are going to assume that our voltage sources are ideal, so that way no matter how many components I add, that voltage of that battery, that power supply is always going to remain the same. So Ohm's law tells us that I0 is equal to V0 over Req, just rearranging what we had before. So if we assume that the voltage of our power supply is constant, that V0 is a constant, the larger my equivalent resistance, the smaller my current is going to be. So what this tells me is that in a series circuit, the more resistors that I add, the smaller the overall current is going to be in the circuit. So let's take a look at parallel circuits. So with our parallel circuit, we are going to have multiple loops. So we can take this image that we have here of our light bulbs, and we can make that in a circuit diagram look like this guy right here. So you can see that we have different loops. I have a loop here, and I have a loop here. And then I also have that third loop here, but I don't usually worry about that loop. So in this case, we're going to start with Kirchhoff's loop rule. So this tells us that the sum of our voltage rises and drops is 0. So once again, our voltage rise is caused by the battery and our voltage drop is caused by those resistors. Choosing a loop direction. Now, we usually do a loop for every component and that is possible with the battery. So the loops I tend to draw are the loops that include the battery. So looking at this first one, my voltage rise is going to be V0, my voltage drop is going to be negative V1. So when I write that loop rule, I get positive V0 minus V1 is equal to 0. I could choose the second loop, which includes R2, and I'm still going to get a voltage rise of positive V0 and a voltage drop this time of negative V2, and that has to equal 0. So if I rearrange these, this first equation right here tells me that V0 has to equal V1. This one right here tells me that V0 also has to equal V2. So that means that V0 is equal to V1, which is equal to V2. So basically every branch that contains the battery and a single component is going to have the same voltage as the battery. And the way I picture that is if I picture this side of the power supply has 0 voltage right here, then this whole wire, all the way until I get resistance, until I hit a component, that whole wire has to have a voltage of 0. If I assume the positive side of my battery is positive V0, then everywhere along that until I get to a resistor has to be positive V0. So I can see that the difference in potential for resistor R1 has to be V0 minus 0, which is just V0. The difference in potential for resistor R2 also has to be V0 minus 0. So as long as each component is in its own individual branch, all of those voltages are going to be the same. And they will all equal the battery voltage. Now, if we look at the junction rule for the parallel circuit, we do actually have legitimate junctions where our current is going to split. So the junction rule tells that current into a junction has to equal current out of a junction. So you can pick a junction and you can write an equation for that. So I'm going to assume that I1 is the current going through resistor R1, I2 is the current going through resistor I2, and I0 is the current in the main branch that's being drawn from the power. So the overall current draw from the battery. So if I look at that junction, I can say that my current in, which is I0, is getting split into I1 and I2. So that equation would be I0 is equal to I1 plus I2. So the current draw from the battery is the sum of the currents in each branch. Now, what happens here with equivalent resistance, if I was to try and replace this with a single resistor that still has that same current I0, I get that my equivalent resistance is 1 over Req is equal to 1 over R1 plus 1 over R2. Now, where we get this from is starting with our current rule. I0 is equal to I1 plus I2. Once again, I can write statements for Ohm's law for each component. I can state that I0 is going to be V0 over REQ. I can write that I1 is going to be V1 over R1, and I2 is going to be V2 over R2. I can then take those and plug them in to my junction rule. So I0 is going to be V0 over REQ. I1 is going to be V1 over R1. Oop, not plus, sorry, hold on. Plus V2 over R2. Now, our big assumption here when we were in parallel was that each of these branches has the same voltage as the battery. So V1 can be replaced with V0. V2 can also be replaced with V0. And then I can see that each of these terms has V0 in the top, so they all cancel down to 1. So if I was to divide this whole thing by 1, I would get 1 over REQ is equal to 1 over R1 plus 1 over R2, plus however many of those that I add. So if I wanted to actually find REQ, though, you just have to remember that you have to take the reciprocal of that term in order to actually finish out the calculation. Now, if you add more resistors in a parallel circuit, this tells us that our resistance in the circuit actually decreases. You could prove that by plugging in some example numbers. So, for example, I'm not going to plug in numbers, but I'm just going to assume that those two resistors, R1 and R2, that they just have values equal to R. So if I was to do this 1 over REQ, I would get 1 over REQ is equal to 1 over R plus 1 over R. So I would combine the terms, so I get 1 over REQ is equal to 2 over R. And then if I take that to the -1 on both sides to flip that, I get that REQ is equal to R over 2. So if I just had one resistor, with one resistor, my resistance would just be R. With a second resistor, my resistance is R over 2. And I can see that if I keep adding more resistors, my equivalent resistance is going to get smaller and smaller and smaller. And the reason for that is I'm actually creating multiple paths for the current to pass through. So it's almost like making my wires fatter and fatter and fatter, because we said that our resistance is equal to rho L over A. And we basically said if our cross-sectional area gets bigger, our resistance goes down. So what we're doing is we're kind of like taking that junction and splitting that off and coming up with each individual wire. So each path is basically adding up to that cross-sectional area that the current can flow through. It's kind of a simplified analogy, but that's really what's going on, is we're creating multiple paths for that current to flow through. Now, we still remember that the voltage of the power supply must remain the same. So when we look at Ohm's law, our current draw from the power supply is going to be V0 over REQ. So this time, if our power of our voltage source is constant, and as we add more components, our equivalent resistance goes down, that's going to cause the current draw from the circuit to actually increase. So the more components we add, the more current gets drawn from the battery. So if we compare these, series versus parallel, for current, we're going to have in series the same current through every component, and it's equal to the current draw from the battery. In parallel, our current through each branch is going to add, and the more and more components we have, the more and more current draw we have from the battery. The voltage in series of each individual component has to add up to equal the voltage of the battery. Sometimes we call resistor voltage divider because you take the voltage of the battery and you divide that voltage up amongst the components. So therefore, the more components you add, the smaller and smaller the voltages each component has, because the total voltage has to remain the same as the voltage of the battery. In parallel, as long as each branch has only one component, each branch is going to have the same voltage as the battery. With resistance, adding more resistors increases the equivalent resistance in series. With parallel, adding more resistors actually decreases the equivalent resistance because it provides more paths for current to flow. When you think of light bulbs, if one light bulb were to go out in series, all the rest are going to go. Picture Chevy Chase in Christmas Vacation. If you've ever done Christmas lights and so forth, and you have done this great display and you try to plug it in and waiting for the glorious lights, but if one's out, they all go out. Now, modern day lights are getting fancy, and you can pay more money for Christmas lights that are wired so that each individual bulb is basically connected to the power supply. So that way, if one goes out, all the others stay lit. But those are usually a lot more expensive than the ones where if you pull one of the light bulbs out of the socket, none of the lights work. In parallel, as long as each bulb is in its own branch connected to the battery, if you take one out, the others are still going to stay lit. So overall pros of the series circuit is that your battery is going to last longer because there's a lower current draw. So remember that power is related to energy. So our power is current times voltage. So because our voltage is determined by the battery, okay, this is assumed to be constant no matter how many components you add. So if you have some amount of battery supply, your current is lower, so that means your overall power draw is lower. And remember that that energy is power times time. So a longer period of time with a lower power is going to be a lower energy usage. So if you want a battery to last longer, you need to put them into series. But you have to make sure that your current draw is not too low, otherwise your devices that are plugged in won't be able to function. The pro of the parallel circuit is that brighter light bulbs the light bulbs themselves are going to be brighter because each bulb is going to get the same voltage of the battery. So each bulb that you have is going to have the same brightness as an individual single light bulb would have. So if I was to take my battery here and put a single light bulb in, that light bulb, as long as it has identical resistance to the next one, is going to have some sort of brightness. And you could do this using the PHYS circuit simulation that you use for the lab. You can test this out. And then if I was to add another one in, you would think that adding more bulbs in would cause this first one to get dimmer, but it isn't, because this guy gets the full voltage of the battery, because this from here to here is the same voltage as from here to here. Assuming that our wires have no resistance, then this one would be the exact same brightness. So I could actually keep adding light bulbs in, and each of my light bulbs would have the same brightness. Now in reality, because our wires don't actually have zero resistance, they have some small amount of resistance, adding in this extra branch has actually added to the overall resistance in the circuit. And you'll have, if you do this in real life, which I've actually built some of these before for demonstrations, for in-person classes, you find that there is a little bit of dimming the more and more that you use. But it's small compared to kind of what you would expect to see in series. Because in series, if I take a light bulb and I put it here, and then I add another identical one, what happens is these are going to be half as bright as any one of those. So brightness is going to be a big deal when you start looking at that. Now, when you look at cons, as I just mentioned, the light bulbs in series are going to be dimmer since each bulb is going to get part of the battery voltage instead of the whole part of the voltage. Now, this is actually a safer way to operate. Most components have a maximum voltage, and if you exceed that voltage, they burn out. It's pretty easy to do that with little light bulbs in a circuit. So you do have to be careful with that. So series circuits are actually a little safer in terms of each component itself having a smaller voltage draw. With parallel, your battery is going to die a lot faster since you're going to have a much higher current draw. So your power, once again, is current times voltage. So with the voltage of the battery, you're going to have a much higher current, so you're going to have a larger power draw, which means you're going to use more energy in a particular amount of time, and you are going to end up draining that battery fast. And if you take, say, like a standard 9-volt battery that you would use in a physics lab and plug 3 or 4 light bulbs into it, just the little tiny like ones that they use for physics, you're going to find that that battery will completely die in about 30 minutes. So good thing, because it can give you that higher power per component, give you brighter light bulbs, but you're going to use a lot more energy. So if you're not on like a fixed power supply, like what's coming out of the wall, you're going to end up with issues. So what can we do with all of this? So we're going to start looking in our next video about more complex circuits. You could use Kirchhoff's rules to rank the brightness of light bulbs, or to rank the current through a light bulb, or the voltage drop across light bulbs. You could calculate the current, voltage, and resistance for the whole circuit or for individual components in the circuit, also power, energy, and things. And then, of course, we're going to shift and start adding in capacitors and inductors into these circuits as well.